In this video, we're going to find the center of mass, and along the way, we're going to need to find the total mass of a non-uniform rod. So for my sample problem, I said, hey, let's find the center of mass of a rod of length L, whose linear mass density is given by the function 3x plus 7. I just put the units on there, so it come out to be kilograms per meter. So kilograms per meter squared times meters, right, would give you kilograms per meter. Anyway, where the left end of the rod is at x equals 0. So that's what our picture looks like. So again, this is going to be very similar in setup to the problem that I just did with finding the center of mass of a uniform rod. Here's that uniform rod problem. With this one, we said, hey, uniform rod of mass m and length L, find the center of mass. So we said, hey, we'll use the integral form of the center of mass equation, going from x is 0, from 0 till we had the total mass and the object all added up. Again, taking each little bit of mass times its position and adding up to, and then dividing by the total mass. That's the way you find center of mass. We're going to do that same trick here. Am I going to copy it down to have a fresh copy? Or am I just going to point at this old one? I'll copy it down to a fresh copy. So we're going to go about doing this. Okay, I'm going to do it side by side here. And so you'd say, sure. If I want to use my cool center of mass formula, my integral form, I'm going to say, yeah, let's find the center of mass of this guy. I'm going to take 1 over the total mass times the integral of x dm from 0 until I've added up to the total mass of the object. I might go ahead and set up like this and say, yeah, sure, 1 over the total mass. Again, I realize I'm going to take this rod and I'm going to slice it up, slice, into a bunch of little pieces. Slice. Each one of these little bits here is a little dm, and it has a width here that's dx along that x-axis, right? And I'm going to think about my mass per length to find the relationship between mass and this little distance along the length. So again, I'm going to use my linear mass density. But the thing here that's weird is that before I could say, because of a uniform rod, I could say my linear mass density is my mass per length. And so I just take the total mass divided by the total length because it was uniform, because it was the same all the way through. That's not the case here. In this case, as I go along, as x gets bigger, it becomes more and more densely packed, the material. I think before I talked about maybe taking a tube and filling it with snow and then thumping the tube on its end, thump, 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 and the snow kind of settles down. It gets more densely packed at one end and less densely packed at the other. That's the sort of thing going on here. It gets more dense as we head to the right end. So it's not, the lambda value isn't a constant. It's changing as I go along. But I still want to go ahead and do that substitution. It's just that lambda, I can no longer take the total mass divided by the total length and get lambda. That would be some sort of weird average lambda or something. You see, what I want to do here, though, is I want to have, as I go from bit to bit to bit to bit along the length, changing x, I want to go ahead and get the density at each little bit. So my lambda, it'll be the mass per length, right? That ratio, but it's not going to be a constant value. So rearranging dm will still be lambda dl. And again, a dl is going to be the same thing as a dx in this case, because the length is along the x-axis. So I'm still going to do that lambda dx substitution for dm, right? So again, I'm substituting in lambda dx. And my bounds, again, are going to go from x is 0 to x is L. Again, I'm changing the bounds of the integral, okay, so that my bounds match my new variable of integration, x instead of m. but they still correspond to the old bounds. I'm still going from here to here, adding up all the mass in the whole thing. I'm just going from x is 0 to x is L to do that. Okay, this is the exact same thing that we have here. What's going to be different is this next step. In the next step, lambda, we could factor it out of the integral because it was a constant. But in our new problem, lambda is not a constant, so it will not factor out of the integral. We're going to need to swap in where it says lambda. We'll swap in, well, we got to say what it is. You say, well, lambda was given to us as a function here. It's 3x plus 7. So the difference here is lambda is not going to factor out, the first difference. There's another important difference to come here. I'm going to swap out, I'm still going to go from 0 to L. You say, but where it says lambda, I'm now substituting in that function they gave me, 3x plus 7. Okay, and that's the integral I need to take. And now it's an integral just in terms of x, which is what I needed, just one variable. And so I can integrate that mess. Let's stop with the color coding, and let's go ahead and take that integral. Let's see, 3x squared plus 7x, right? dx. And so you say, hey, don't forget that 1 over m on the outside. Okay, and say, hey, taking that, again, I'm doing a derivative in reverse. You say this would be x squared would go up. Before it was took the derivative, you would have an x cubed. If I took the derivative of x cubed, it would kick a 3 in front, just like I have there. This would be, I'd have an x squared. If I took the derivative, kick a 2 out. I don't have a 2, I have a 7, so there must have been a 2 in the denominator there, right? I'm going to evaluate that from 0 to L. And I still have that 1 over m out in front, right? Whoops, I went down. I'm so sorry, I went way down off the bottom edge of the page. Sorry about that. Again, taking my integral, swapping in the function 3x plus 7 for lambda. I just went ahead and I just distributed that x. Took my integral, the x squared would have been x cubed. When I took the derivative of x cubed, it would have kicked a 3 out in front. Hey, there is a 3, it's all good. Integral of 7x is going to be 7 halves x squared. Again, all good. Evaluate from 0 to L. And so I'm going to end up with something that looks like this. L cubed plus 7 halves L squared, right? And at this point, you might say, hey, is that my answer? Is that my position of the center of mass? And you say, well, it would be, except for the fact that we weren't given m. We weren't given the total mass of the rod. They just told us the density function and that the length was L. And so we actually have to stop and quickly figure out what is the total mass of the rod. So that's going to be a separate little calculation I'm going to have to do off to the side here and then substitute it in there for m. Okay, but we see the difference between the old technique and the new technique here. You say, hey, with this variable linear mass density, I can't just factor the lambda out. I'm going to have to put the function in and take the integral of that. The other difference is we need to figure out m. So here's the way that I find the total mass. The way I find the total mass is I say, well, if I want to find the total mass of this thing, isn't it true that I can find the total mass if I added up all the little dm's, the slice, and all these little dm's from m equals 0 to m equals big M. That's what I'm going to do. But where it says dm, I'm going to sub in what? Not take an integral in terms of mass. I'm going to take an integral in terms of, again, position in terms of x. Again, I'm going to use lambda again, my linear mass density. And I'm going to say, hey, that linear mass density, again, it's not a constant. It's going to be dm to dl, not m over l. And so I'm going to say, yep. So I'm going to do that substitution again with the linear mass density. And again, I'm going to rearrange and say, yeah, that means dm is lambda dl. And yeah, I'm going to say that dl and dx are the same thing in this problem. And so this is a substitution I'm going to make. And so my total mass is going to be the integral now of lambda dx from x equals 0 slice to x equals L. Again, changing my variable integration to x means my bounds have to change to match and still correspond to the old bounds. Again, the lambda is not a constant. It won't just kick out, which is why I have to mess with this integral thing, because it's changing as I go along smoothly. And so you say, hey, where it says lambda, I'm just going to put in the function. Am I going to stop color coding now? Yeah, I am. Let's stop color coding. So I want to take the integral from 0 to L of 3x plus 7 dx. Okay, and integrating that, you say, hey, that's going to be up a power. It would have been x squared. When I take the derivative, we kick a 2 out in front. I don't have a 2, I've got a 3, so there must have been 3 halves x squared plus 7x evaluated from 0 to L. And you say, hey, that's going to be 3 halves L squared plus 7L. And that is the total mass. Again, if I had a value for L, I could plug it in. I just went off the bottom of the page again. Sorry about that. I keep doing that. Dang it. So I just put the function in for lambda here, because lambda is not a constant. I couldn't just factor it out. 3x plus 7. Took my integral, subbed in my bounds. You say, hey, that's what the total mass is. Again, if I had a value for L, I could just substitute in. Like, for example, if L was 1, if it was a 1 meter long rod, this would be a total mass of 3 halves times 1 squared plus 7 times 1. You say, hey, that would just be 8.5 kilograms would be the mass, the total mass of the rod. So that's the way that we find the total mass. I just imagine slicing a bunch of DMs and then add up all the DMs until I have the total mass of the rod. I can take my integral, in this case, in terms of linear mass density, and get my function. Okay, see, now I know what total M is. I could put that back into, here was my work, into my equation here for this non-uniform rod. I can just substitute this in where it says M, and then I'm in business. And so my center mass, say, hey, that's going to be this L cubed plus 7 halves L squared. And then in the denominator, I've got this total mass that I calculated here, 3 halves L squared plus 7L. Yeah, I could tidy this up a little bit, and I could maybe factor an L out of everything, an L at the top and L out of the bottom, and cancel. And then I'll have what? L times L plus 7 halves, right? Over factor an L out, cancel one, the L's on top, 3 halves L plus 7. Okay, and I realize that this is not like an especially meaningful answer. I mean, I just picked a random function, 3x plus 7. I didn't do anything fancy. Again, if we knew the length of the rod, we could plug in, like, for example, simple case, if L was 1, then you say, hey, I would get 1 times 1 plus 7 halves, 1 plus 3.5, that would be 4.5 divided by 3.5 plus divided by 8.5, and 4.5 divided by 8.5 gives me a center mass just a little bit to the right, yeah, just barely to the right of middle. Okay, which seems reasonable. Okay, again, if I had a different length rod, I would get a different center of mass. But yeah, but that's it. That's actually the center of mass equation for this one. So we did two things. We had to do a calculation for for the total mass, because it didn't give that to us. You notice again, this integral and this integral, right? They end up being very, very similar math, right? There's just an extra x in there. You know what I mean? Okay, as I go through and work it out. It's the same techniques, using that linear mass density to substitute. Okay, that'll do it for this one.